We're recording. So on this last example, we're going to put into practice all of these little steps that we kind of went through up here. And when you eventually take your quiz, this right here will be given to you. It'll be projected, or I'll show it to you. Yeah, yeah. I might have to run off a private copy for you. I won't be here on Monday or Wednesday. I got some doctor's visits that I have to attend, so you'll have someone here to hand you the quiz, someone here to hand you the test. And since they won't know how to project this up on the screen, I might just have to run out a class set of these. Okay, but you can have it on your desk as you go. I do want to point out these horizontal or slant asymptotes. I mentioned yesterday that these are your end behavior asymptotes for very large value of x. Like when you look off to the left-hand side of the graph or the right-hand side of the graph. Remember, there's three scenarios. If the bottom grows faster, it's always going to have a horizontal asymptote at y equals 0, always. So that would be like x squared over x cubed, x to the first over x squared. As long as the bottom's a larger degree, HA is always at y equals 0. If the degrees are the same, x cubed over x cubed, whatever, x to the first over x to the first, there's a horizontal asymptote at y equals leading coefficient over leading coefficient. So there's two ways to get a horizontal asymptote. You get a horizontal asymptote this way, that always at 0, and you get a horizontal asymptote this way. The third way is not a horizontal asymptote. This is a slant asymptote. If the top is bigger by 1 degree or bigger by any amount, you're going to get a slant asymptote. Now, I told you yesterday that you're not going to have to worry about slant asymptotes, but that's a lie. I actually combed through the homework, and there is one question where you're asked to find the equation of the slant asymptote. Now, how do you find the slant asymptote then? Well, you do division. And the quotient only, not the remainder, is the equation of the slant asymptote at y equals mx plus b. At y equals mx plus b. So let's say you have x squared plus 2x minus 3. Here's an example. All over x plus 1. Okay? You can do synthetic division here. The top is bigger than the bottom. You see that? The top is bigger than the bottom. So there's no horizontal asymptote. But there is a slant asymptote. So you write out the coefficients, 1, 2, negative 3, and you synthetically divide with a negative 1. You bring this down, you get 0. You get negative 1, sorry, you get 1. You get negative 1, you get negative 4. This right here, these are the coefficients of your slant asymptote. So this would have an SA at y equals 1x plus 1. And you're done. Slant asymptote at the quotient without the remainder. There's one question in your homework where you have to do that, okay? So now you know how to do it. But mainly we're interested in the horizontal asymptotes, either at 0 if the bottom is larger or at the leading coefficient if they're the same. Okay, all right, let's go ahead and do this last one here. I told you the first thing to do is to factor it. I like to answer these in a particular order. So for factoring, we look for a common factor first. There is no common factor in the top. The bottom is a double bubble. Okay, the bottom is a double bubble. It looks like it's going to be x plus 4, x minus 2. You see that? X plus 4, x minus 2. Now, the reason you want to factor is for the domain. There are two factors in the bottom, x plus 4, x minus 2. The values of x that make the denominator 0 are not going to be in the domain. So, right away, we know that x cannot equal what value from this one? Negative 4. Good. And x cannot equal what value from this one? Positive 2. Okay, to get the roots from the factors, it's the opposite. X can't be negative 4, it causes a 0 in the bottom. X can't be 2, it causes a 0 in the bottom. Guess what? We just found our domain. So let's come down here and we'll answer the domain. It's the set of all x such that x is not equal to negative 4, comma 2. All right? No way, no how. They're going to be in the domain. Now, here's what's new to this problem and this section, okay? These are going to be called discontinuities. Discontinuities are zeros in the denominator. Zeros in the denominator. Anything that causes a 0 in the denominator is going to be a discontinuity. A discontinuity does exactly what you would think it does, having a name like discontinuity. It interrupts the flow of the graph. There are two types, okay? There's two types. Number one, you have the vertical asymptote. We know what a vertical asymptote does, right? The graph would look like this on one side and maybe like that on the other. There's no way to get around that vertical asymptote. It interrupts the flow of the graph. But the other type is called a hole, which is also known as a removable point discontinuity. That's what I mentioned up here, a removable point discontinuity. Okay, but you can just call it a hole. It looks like this. It interrupts the flow of the graph like that. Now the difference is a vertical asymptote is at x equals a. It's an equation of a vertical line, whereas the hole is a coordinate a comma b. It's a hole. It's a coordinate. So there's one other task to do besides identifying that it's a hole. We have to find the y value. Now, remember how we find a vertical asymptote. A vertical asymptote is anytime you plug in and you get non-zero over 0, or you get something like x minus a, and then in the top you have like x minus b times x minus c. Okay? This does not divide out. Does not divide out. If your factor that causes a 0 in the bottom does not divide out, you have yourself a vertical asymptote. On the other hand, if you get 0 over 0, I told you yesterday to write it like that, it's a hole. Okay, you get 0 over 0. That means you have an x minus a in the bottom, but you also have an x minus a in the top. And there could be another factor like x minus b. And you can also have a factor down here like x minus c, whatever. But what's important is that they do divide out, okay? They divide out. If it divides out, it's going to be a hole. If it doesn't divide out, it's going to be a vertical asymptote. That's how you can tell which is which, okay? So you first look, does it make the denominator 0? Yes. So those are not in the domain. They're both discontinuities. What type are they? Does it divide out? Yes, it's a hole. No, it's a vertical asymptote. If it does divide out, I'm going to show you how to find the y value of the hole. Okay, so let's look at this one a little more carefully now. I do see that I have an x plus 4 in the top, and the x plus 4's divide out. Yes, yes? See that? That leaves a what in the numerator? A 1. Okay, now here's what's important. Once those divide out, you can write the equation of everything that's left. Okay, and we're going to use this for the rest of the problem. We don't look back, okay? We identified that there's a hole. So here's what I'm going to say. There's a removable discontinuity, also called a hole, at the coordinate -4, comma what? Okay? Here's how you find the y value of the hole. You basically take the x value that caused the 0 and you plug it into what's left. You take the x value that caused the 0 when the factor was there, and you plug it into what's left after you divide it out. Let's see what we get. At x equals 4, or x equals -4, what do we get? We get 1 over -4 minus 2, which is 1 over -6. See what I did there? I factored, I divided out, and then I plugged it right back into what was left over, and that y value gives me the y value of the hole. So I can write it as -4, comma, -1/6. And we got it. We got the y value of the hole. All right, now what's the vertical asymptote? This one doesn't divide out. There's no way to divide out the x minus 2, so this would be a vertical asymptote. So if I come down here to the VA, I have a VA at x equals 2. If it divides out, the root is a hole, find the y value. If it doesn't divide out, then the value that causes a 0 is a VA, call it x equals that value, okay? That takes care of the VA, that takes care of the hole. Now, since we're talking about asymptotes, we might as well look at the other type of asymptote. Now, as this diagram that is going to be given to you on Monday and on Wednesday shows you, if you want to find the horizontal asymptote or the y-intercept, you want to look at the original version. If we call this the original version of the function, it's the expanded version. This would be the factored version. The reason is that certain versions are more useful than other versions for different things. It turns out if you're interested in the horizontal asymptote or the slant asymptote, you want to look at the original version. And it's a lot easier to find the y-intercept, although it's not required, from the expanded version as well. Okay? So let's go ahead and find the horizontal asymptote. I come back here to the original version, and I compare the leading coefficients. Or the leading terms. There's the leading term. There's the leading term. You get a horizontal asymptote in two cases. When the degrees are the same, is that the case here? Are these degrees the same? No. Or when the bottom is bigger, is that the case here? Yes. So anytime the bottom is bigger, the bottom grows faster. What did we say about the horizontal asymptote? Where does it go? It goes to zero. When the bottom has a larger degree, it goes to zero. So we know we're going to have a horizontal asymptote here. I'll just say HA at y equals zero. Make sure you put y equals. That's also known as the x-axis. Okay. Now let's do a real quick what if. What if this were actually x squared plus 4 over x squared plus 2x minus 8? Now the degrees would be the same. Yes, yes? And now it would be leading coefficient 1 over leading coefficient 1. Now we'd have a horizontal asymptote at y equals 1. See the difference? Okay, that's just a review. That's not what we have here, so I'm going to backtrack on the purple stuff. Okay, so we actually have a horizontal asymptote at 0. The last two things that we need to find are the zeros, okay? And for these, let's find the y-intercept first. The y-intercept is easier. Yeah, the y-intercept is easier. So all you got to do is let x equal 0. Now, as it says up here on this little chart that you're going to be using, it's easy to find the y-intercept from the original version. So let's stick with the original version, okay? You can also do it on this right here if you want. You can also use 1 over x minus 2. But the reason you want to use the original version is because when you plug in a 0 for x, every term that has an x in it is gone. You get 0. So you're left with 4 over negative 8. What's 4 divided by negative 8? Negative 1/2. Yeah, very good. So it's just easier to do that. You could also plug it in over here. What do you get when you plug in a 0 for x right here? You get 1 over negative 2, which is negative 1/2, right? So it doesn't matter which one you plug into to get the y-intercept. So let's write the y-intercept. I'll write it as an ordered pair. 0, negative 1/2. That's a point that we can actually plot. Now, for the zeros or the x-intercept, you're going to want to set the new numerator equal to 0. We haven't done this yet where our factor divided out. We want to set the new numerator equal to 0, not the old one. If you set the original numerator equal to 0, you're going to get negative 4 as an x-intercept. Negative 4 is not an x-intercept because there's nothing there. It's a hole. So here's the new version. If you want to call this the new version, you set the new numerator equal to 0. Well, what's our new numerator? 1. So let's set that equal to 0. Does 1 equal 0? No. So guess what? If there's no solutions, how many x-intercepts do we have? None. If that happened to be x or x plus 1, you would then solve it, okay? You would solve it. So I think we have enough information to plot. The range is always the last thing that we do. We get it from the graph. All right, now if you haven't been plotting your information as you've been finding it, now's the time to put it all on the graph. Do your asymptotes first, though, okay? Your asymptotes go first. I got a vertical asymptote at x equals 2. So I'm going to come in here and draw a vertical asymptote at x equals 2 all the way through. And I got a horizontal asymptote at y equals 0, which looks like this. And now I have some points that I can plot. You either plot x-intercepts, y-intercepts, or holes, okay? And if you want to, you can always pick a random x value and find the y value. We talked about that yesterday. You can make a t-chart if you want with random x values. But we're trying to do it as efficiently as possible. There is no x-intercept to graph, so there's a missing opportunity for a point. And I have a y-intercept at 0, negative 1/2. So that's going to be right here. That's a point on the graph. The hole, remember, was at negative 4, negative 1/6. So I come over here to negative 4. Negative 1/6 is going to be just below the x-axis. Not even quite down as far as negative 1/2. It's just below the x-axis. So I'll draw that as an open circle. Okay, now, if you look, I have one vertical asymptote. To the left, the graph is either going to live above the horizontal asymptote or below. What do you think the case here? Does the graph live above or below to the left of the vertical asymptote? Below. There's two indicators that it lives below. So let's go ahead and draw a line coming from the horizontal asymptote. We'll draw it going through the open circle. We'll go through that point there, and then we just turn rapidly and go down towards negative infinity. So there's what one of the branches looks like. Now, to the right of the vertical asymptote, we have no indicators. We don't know if the graph lives above or below. So in order to help ourselves to indicate what's going on, feel free to choose any x value you want to the right of 2. And then once you know its y value, you'll know if it lives above or below. So I'm going to choose 3 because it's the smallest integer of the values to the right of 2. If I know the function value of 3 is positive, it lives above. If I know the function value of 3 is negative, it lives below. Now, here's what's cool. You can use the new version for that calculation. So what's f of 3? I plug it in, I get 1 over 3 minus 2, which is 1 over 1, which is 1. So that's the 0.3 comma positive 1. Oh boy. So I know it lives above. So I'm going to come here at 3, 1. I'll just put a dot there. And now I know what the graph looks like. I can come from infinity, pass through that point there, turn sharply, and start heading towards the x-axis. And now you have your graph. And that's a beautiful graph. You're done. Now, there is another way for this specific problem that you could have figured out what the graph looks like. Remember I said once you get rid of the hole, you can use this new version for the entire rest of the problem? Don't we know what 1 over x minus 2 looks like? Isn't that just our parent function 1 over x scooted to the right 2 units? Yeah, that's exactly what I have drawn here. It lives in quadrants 1 and 3. It's scooted to the right 2 units. The only difference is what? It's not 1 over x minus 2, because 1 over x minus 2 doesn't have a hole there. And this one does have a hole at negative 4, negative 1, 6. The reason it has a hole there is because someone added an x plus 4 factor over an x plus 4 factor. Hey, just while we're at it, if I wanted to add a hole, let's just go ahead and say for the sake of argument, what if we're playing Swiper right now? What if I wanted to add a hole at x equals 4? If I wanted to add a hole right here at x equals 4, so I wanted to come in here and I wanted to swipe out that ordered pair and turn it into an open circle, what would I need to add to my equation to generate a hole at x equals 4? How did we get one at x equals negative 4? Well, there was a factor of x plus 4 in the top and a factor of x plus 4 in the bottom. So if you want to get a hole at x equals positive 4, all you got to do is add a factor of x minus 4 to the top and x minus 4 to the bottom. You can just listen to this. You don't have to write it down. That's enough to give you a hole at x equals 4. What if you wanted to get a hole at x equals 5? What would you add to the top and bottom? X minus 5, x minus 5. You can make this thing as holy as you want by just putting x minus the number over x minus the number, and you can have this graph like Swiss cheese if you care to. Okay? So that's how you add holes to the graph. We added one at negative 4 by putting x plus 4 over x plus 4. All right. So alas, this is not what the graph looks like, so I'm going to go back. There we go. The last question we answer is the range. All right? The last thing we answer is the range. What y values does this graph take on? It's the set of all y's such that. If you notice carefully, we get all the y values from negative infinity to positive infinity except 2. There are 2 y values that we don't actually touch or obtain. Any idea what they are? 0, right? We don't get y equals 0 because there's a horizontal asymptote there. So we don't get y equals 0. And what other y value do we step over, if you will? Negative 1, 6, right? That's the y value of the hole. The y value of the hole. So we don't get either one of those. So that's it. So you say y is such that y is not equal to, and you could write them in any order. Negative 1, 6, comma 0, or 0, comma negative 1, 6. We get all the other y values on this graph. And we're done. For the sake of reviewing here quickly, let's just answer this quick question. As x goes to infinity, what do we call this function? F of x? What does f of x approach as x goes to infinity? Hop on the graph, start heading out to the right forever and ever and ever. What are the y values getting closer and closer to? 0. Yeah, that's what that question means. And then the last one I'll ask you, as x approaches 2 from the left-hand side, what is f of x approaching? As we approach 2 from the left-hand side? Negative infinity. Yeah, it's going down towards negative infinity. Very good. Hey, here's one that I can ask you. What is, as x approaches -4, what are the function values approaching as we approach -4? No. As we get closer and closer to -4 from either side, the y values are getting closer and closer to the whole, aren't they? What's the y value of the whole? -1/6. Do we ever get to -1/6? We can get to -1/6. If you get to -1/6, you're going to fall in the hole. We don't want to do that. But as x gets closer and closer and closer to -4, we get closer and closer to the y value of the whole, which is -1/6. Yeah, there you go. Okay, so you have the rest of the period to work on your assignment, and I'm going to pass back your quizzes. Don't show them to someone who hasn't taken the quiz yet. If they say, "Hey, can I look at your quiz?" Ask them, "Have you taken the quiz yet?" And if they go, "Yes," like that, say, "You're kidding. You haven't taken it yet." And don't show it to them. Yes, yes. All right. And I'm up here to answer questions you have on the homework or the quiz. Got it? All right. We review tomorrow. We quiz on Monday.